Good morning, everyone. Welcome to our session on models and tools to move from data to decision making. Basically, data does not speak, so we need to come up with a story to tell with. So that is what we are learning with this session. Today, in this session, we will be exploring innovative approach and state-of-art tools designed to bridge the gap between complex data and practical decision making. Our distinguished speaker will present their groundbreaking research and methodologies that support adaptive management, climate action, and sustainable resource management. That covers whole of this presentation. My name is Sailesh Adhikari, and I work at the USDA Forest Product Laboratory, and I will be serving as the moderator for this session. And I'm thrilled to be moderating this session together with Joe. And I hope if Joe can introduce himself, that will be great. Joe?
Yeah, hi. This is John McCollum. I'm computer scientist with FIA, Knoxville, Tennessee.
Oh, thank you, Joe. Okay, so to begin with, our first presentation, it is titled as Accounting for Uncertainty in Models of Forest Dynamics to Inform Adaptive Management Decision. This is the presentation by Dr. Malcom, and this research is more about exploring Bayesian dynamical model that address the crucial need for quantifying, prioritizing, and propagating uncertainty in prediction of forest dynamics. So let's welcome Dr. Malcom. Malcom, the floor is yours.
All right. So thank you very much for the introduction. I'm going to talk a little bit about some of our recent work to better account for uncertainty in models of forest dynamics, and then how we can bring that uncertainty to bear on our adaptive management decisions. Okay, so just a little bit of background. Models of forest dynamics are really an essential tool for assessing changes in forest ecosystems over time and space. We can use predictions from these types of models to help us better understand forest responses to global change, as well as to test alternative adaptive management strategies. And then particularly important, sort of the current climate, thinking about forests as a climate mitigation resource, to estimate future levels of carbon storage and sequestration. So the challenge here is that, global change is already contributing to fundamental shifts in our historic forest dynamics. And this really has a couple of important consequences with impacts on how we think about sustainably managing our systems. And so the first is that we have increased uncertainty in the demographic processes that underlie forest dynamics. And then secondly, the historical patterns of forest dynamics that have served as the basis for sustainable forest management for the better part of a century aren't necessarily good indicators of where those forests are heading. And so again, we have increased uncertainty in the future of our forest system. So there's been rapid development of models of forest dynamics over the last couple of decades. And this development is focused on two primary areas. The first would be scalability. So we think about the simplest models of forest dynamics back in the day would have been running at an individual site, so a stand scale model. And now we have models of forest dynamics that are able to make predictions of these processes at a global scale. And then the second piece is sort of increasing the ecological detail, the ecological complexity that's represented in those models. And that's sort of highlighted in that figure on the left there in this recent review paper by Bugman and Siddell that sort of just highlights the increase in the model complexity in these sorts of models over the last, say, 50 years. But despite that sort of increase in sort of the ecological detail that's included in our models, we still have large variability in our predictions of forest dynamics under global change. And sort of that figure on the right is sort of highlighting some of this variability, looking at just small changes to several models of forest dynamics and what those changes can do in terms of varying the predictions of future forest ecosystems. In this case, what was being varied there was just the mortality submodel in these models of forest dynamics. And particularly worrisome is that we see the variability increase under different, as we start considering the role of climate change as a driver of these systems. So we can think a little bit about how uncertainty is actually dealt with or quantified in current models of forest dynamics. And so here we have some hypothetical training data. So this could be large scale forest inventory data such as the FIA, and we're using that data to inform some model of forest dynamics indicated here by FDM. And so I have data puts a hat on our model parameters. So we're going to take that inventory data and use it to generate estimates of some demographic parameters that represent growth, mortality, regeneration in our regional forest system, our regional forest system as indicated by theta here. That's just going to be our sort of hypothetical set of parameters. And so once we've got that model parameterized, essentially we're going to plug in our parameter estimates and make predictions of future forest conditions at different locations and time points. And importantly, with this sort of plug-in approach, we're plugging in our model parameters, what we get is point level predictions. So we're going to get a single realization or a single prediction of our forest condition at some future time point. And so for reasons I'm not going to get into in the interest of time, it actually turns out it's very hard to quantify uncertainty under these sort of under this plug-in approach. And so the alternative would be to apply some ensemble approach where instead of just getting a single point prediction of our future forest state, we get some probability distribution of future forest conditions. And so importantly, that distribution is going to reflect uncertainty. And the challenge here is that this ensemble approaches tend to be quite computationally demanding. And so we don't see it applied that often. And when we do, it tends to focus only on uncertainty related to our model parameters, so our thetas here. And it doesn't address some of the other source of uncertainty that can be importantly affecting our predictions of forest dynamics under global change, which I'll touch on in a second here. So an alternative approach would be to apply or develop a dynamical statistical model to make predictions of forest dynamics based on continuous forest inventory data, such as the FIA data set. And so this is really what we've been working on developing for the last couple of years. And so here we're using a Bayesian hierarchical approach. So we're interested in making some predictions about forest dynamics. We're also interested in making some inference about the demographic processes and parameters that drive those dynamics, given some set of inventory data. And we can do that with this really nice conditional approach where we say, okay, our inventory data is going to be generated conditional on our latent process, our unknown process of forest dynamics. And then we're going to have a model of forest dynamics that's conditional on some set of demographic parameters. And then lastly, we're going to have some set of models, in this case, prior distributions for those parameters themselves. And sort of highlight this a little bit more clearly, we have a hypothetical forest stand. So we're looking at some forest conditions at a given location and time point. And Z there denotes the latent or unobserved state of that system. And then I'm using Y to denote the observations, maybe inventory observations at that location and time point. And so what this highlights is the fact that we never get perfect observations of the underlying forest state. Our observations, our inventory observations are always subject to some observational error. They're always going to be some noisy realization of that underlying state of the system. And what we're trying to do here is to take that current state of the system, plug it in as an input to our model of forest dynamics conditional on some set of demographic parameters, and make a prediction of the future state of that system. And so we can make this even more explicit by defining a data model and a process model. So here we say, okay, our inventory observation at some location and time point is going to be equal to the true underlying state of the system at that time point, plus some observational error. And then our process model is going to say, okay, the future condition of that forest is going to be equal to our model-based prediction, plus some process error term, sort of reflecting the fact that our models of forest dynamics aren't perfect, and there's going to be variability or uncertainty in those predictions. So why do we like these sort of dynamical statistical frameworks over the sort of common approaches to that I showed earlier to model forest dynamics? Well, the first is that sort of before we had this two-stage process. We were going to calibrate or parameterize our models, and then second stage you're going to be making predictions. On this sort of dynamical frameworks, we have simultaneous calibration and prediction. We have probabilistic estimates of uncertainty in terms of our observation error as well as our process error, but we also have a posterior probability distribution for our model parameters themselves, which gives us some measure of uncertainty in their value. With this framework, we can synthesize multiple forest data types to the extent that it's available. So this might be multiple forest inventory networks. It could also be supplemental data, remote sensing information, LiDAR data, or paleoecological data that might help us add to the inventory data that we have to better understand our process of forest dynamics. And then lastly, but perhaps most importantly, we get assimilation of future data. So that is, as we get future inventory observations from our regional system, we can assimilate that information into our model and immediately get refinement of the predictions and hopefully reduce uncertainty in our predictions of forest dynamics over time and space. So this is effectively what we've been working on developing for the last couple of years. And so this has got a lot of math on it, but I'm just going to I put it here as a high level sort of introduction to the model. It's the only slide that has a lot of math on it. I'm just going to highlight a couple of pieces. So again, this model is designed to work with continuous forest inventory data such as FIA. So we're using some set of network of permanent sample plots, which are telling us something about our forest conditions at given locations and time points. And what our observations here denoted by Y are just going to be counts of trees and given size classes, in this case, given certain diameter classes from different species across time. And then our sort of process variable here is going to be the true underlying stem density. So the true underlying trees per hectare within each of those diameter classes within each species. And so we're modeling those counts. Our data model here, we're modeling those counts conditional on the true underlying stem density, lambda. And then there's an additional phi parameter, which is an overdispersion parameter, and basically allows for there to be, plot level variability in those counts. Again, getting at this observational error component. And then our process model, we have this matrix projection model here, so that basically the true underlying stem density at a given time point is going to be modeled as its value at the previous time point times some propagator matrix H. And then eta there is just representing some multiplicative process error. And so I'm not going to get into the nitty-gritty on the demographic functions that we're using. This is actually sort of not the main focus of the talk, but I just want to highlight that propagator matrix H can be decomposed into several submatrices reflecting growth, mortality, and fecundity, so G, M, and F. And then there's also this disturbance matrix, which I'll sort of touch on in a second, because that's how we're integrating management into the model. And importantly, that propagator matrix is extremely sparse. So we're modeling these complex forest dynamics with very few parameters, and this is important because we want this model to scale across space and time. And then importantly, that propagator matrix is estimated only based off of those population level counts. And so the idea is we want to build our predictions at a stand scale, so our population scale, so it's important that we're using population level data. Okay, so that disturbance matrix, as I mentioned earlier, effectively is how we're going to integrate management into the model. And so we can do this if we have this sort of latent, if we're modeling the latent stem density for different size classes, different species, essentially what we're getting is some realization of the size species distribution within a given forest. And so we can modify that. You can use that size species distribution to integrate complex management approaches, because in this case, all we need to be able to do is specify some target residual size distribution. And that's how we're going to then integrate, modify the forest and the subsequent dynamics that result from management intervention. And so we've been developing this framework using long-term inventory data from the Penobscot Experimental Forest, which is a 1,600 hectare experimental forest in South Central Maine, co-managed by the Forest Service and the University of Maine. And essentially here we're predicting multi-decadal dynamics within 10 management units under 5 different management regimes. So each management regime has 2 replicates. We've got a control where no harvest has occurred since the forest was established. And then 3 different selection systems with different cutting cycles, a 5-year cycle, 10-year, and a 20-year cycle. And then 2 management units where we have 2-stage shelter wood with a pre-commercial thinning post overstory removal. And so just highlight some high-level results here. And so effectively with this modeling framework, what we're getting is predictions of the size species distribution for every time point, every year in our model period, regardless of whether we have an inventory observation or not. So this is just a few select years in the model period. The stars indicate inventory years, so you can see the points in those years are inventory observations of the size distribution within the forest. The solid line is the overall size distribution. The solid line with the gray shading is the overall size distribution, so summing across species. The single colored lines beneath it are individual species distributions. And so with that size distribution, again, we have this very flexible framework for integrating management. And so, for example, here, this is just a single tree group selection harvest that occurred in one of the management units that had a selection system operating on a 5-year cutting cycle. And so you can see there the predicted size distribution across all species, pre-harvest and post-harvest. Again, the points there are inventory-based observations. So in this case, we had inventory observations in the year preceding and immediately following the harvest. And then on the right-hand side, you can see basically, based on the inventory information, estimates of proportion of trees harvested by species, as well as overall, just to give you a sense of what size classes were preferentially removed during that harvest event. So with the model, if we look at, because we have the size species distribution, we can do a lot of interesting things in terms of modeling dynamics, changes in the forest density, composition over time. And so in this case, I'm looking at overall stem density, both aggregating across species with the solid line with gray shading, which is basically the prediction of the overall stem density across the model period. And the gray shading is our estimate of uncertainty around it, our 95% credible interval. And then the colored individual lines beneath it are individual species. So looking at stem density changes in individual species across those 10 management units with different management regimes being implemented. The dashed lines are harvests. So you can see the decrease in the stem density and subsequent recovery post-harvest in these systems. And then if we have this latent stem density, it's actually quite straightforward to map to other stand level variables of interest, whether it be basal area or volume or biomass or carbon, assuming we have the correct or an appropriate allometric set of allometric equations. And so in this case, I'm basically applied the Jenkins biomass equations to convert those latent stem densities into predictions of live above ground biomass within each of those stands. And so there the points are inventory-based estimates of the biomass that we get periodically over the model period, each time that there was an inventory conducted within the PEF. And then the blue line is our posterior mean predicted live above ground biomass density per hectare. And then the shading is our 95% credible interval. And so you can see some interesting things, like when we get an inventory observation, we get shrinkage and the uncertainty is reflected by lower credible interval bounds. So we learn something about the actual live above ground biomass in the forest, and so that reduces our uncertainty in our prediction. The other interesting thing we can do here is we can take those predictions over time and convert them into sort of standard estimates of growth and yield. So in this case, that table is showing you periodic annual increment over the 40-year model period, looking at the tons per acre per year that were accrued in terms of live above ground biomass that were accrued in the forest, and then the yield at the end of the model period. So how much carbon, or excuse me, live above ground biomass there was in the forest per acre in 2014, the last year in the model period. Again, all with probabilistic estimates of uncertainty. Yep.
Just to interrupt you, we have
No more time. Sorry. Yeah, I'll leave it there. That was the last one was just an important thing. So yeah.
But the thing is that we have, our next presenter is absent. So if you want to continue, just summarize in 1-2 minutes, that's okay too.
Oh, okay. Yeah. I mean, all I was going to say here is just that sort of these kinds of frameworks, we like them because they connect to sort of broader Bayesian decision frameworks that allow us to account for uncertainty in our decision-making process in a formal way. They also connect to iterative approaches to forecasting that allow us to refine our models and ultimately reduce uncertainty in our predictions of these complex dynamics. And so that was really all I had. So yeah, sorry I took a little bit too much time there.
No worries. Thank you. Let's thanks Dr. Itter. So again, welcome to all of you who has recently joined for our sessions. If you are joining right now, as we are exploring the innovative approach to transform data into actionable insight, I want to acknowledge our scheduled presenter, Casey Linger. Due to family issue, he will not be here presenting us today. However, you can reach out to him through the OVA platform for more information about his work. And if you have any question to Dr. Itter, you can ask right now when we go for the session break, because as per the rule of this symposium, we cannot just continue with next presentation. We need to take a break, and we'll be resuming in 10:45 for this session. But you should not have to leave the presentation. You can ask question and you can just talk to people. To talk about Casey's presentation, he's talking about the state of Maine high-resolution land cover forest type and forest biomass mapping from multi-source remote sensing and FIA plot data. And this research looks like very significant contribution to our understanding of land cover and forest composition. And as when I read his abstract, he mentioned that the detailed and accurate maps produced are critical for addressing resource management issues and supporting the state's carbon accounting and management strategy. So if you really want to have some more insight on that one, you definitely can reach him directly in the OVA platform. Our next presenter is talking about mapping forest structure and composition cross-border insight from Southeast Alaska to coastal British Columbia. And this research team had highlighted the significant role of the temperate rainforest of the Pacific coast in global carbon storage with this research. And let's hear from Dr. James Lamping, what is their finding and how this whole research is just structured. James, the floor is yours.
Thank you very much. Hi, everyone. My name is James Lamping. I am a postdoctoral researcher at the University of Oregon, and I'm here kind of just to talk about a lot of work that Dan Irvine, Dave Bell at the PNW Research Station, Matt Gregory at OSU, and Melissa Lukash at UO, and I have all been working on for the past few years on mapping forest structure and composition across kind of coastal Alaska and British Columbia. So a little bit of context on the place we're talking about. North American temperate rainforests are primarily located along the Pacific coast. They stretch all the way from the northern part of California through Oregon, Washington, up through British Columbia, and up to the southern part of Alaska. There's some notable conservation efforts that have recently happened in this region, such as the Tongass National Forest transitioning to young growth management. So that's getting away from managing for old growth and managing for younger second growth forests with the aim of sustaining forest ecosystems, supporting local economies, and kind of to comply with ecological and conservation goals. And then just south of that, you have the Great Bear Rainforest in British Columbia. And that the goal of the Great Bear Rainforest is to protect 85% of the forest from industrial logging. They also incorporate indigenous land use planning and promote sustainable forestry practices, as well as the island of Haida Gwaii. They've been using ecosystem-based management for a number of decades now, also with the goal of maintaining ecological integrity, protecting biodiversity, protecting old growth forests, and ensuring long-term health of forest ecosystems. So these forests, they're characterized by really dense canopy of coniferous trees that include species like Sitka spruce. They include western hemlock, Doug fir, and redwood down here on the more southern parts of the range. And they range in productivity. So here you can kind of see a picture of muskeg or wetlands. And so those are lower productive sites in terms of above ground productivity. And they consist of species like lodgepole pine, bright cedar. And then we have much higher productivity sites, such as these really productive old growth stands with really large emergent trees, smaller understory trees, and a really diverse array of shrubs. And these forests are really crucial carbon sinks, with the large trees storing a really large amount of above ground biomass. But something that's lacking in this region are really high resolution, spatially complete estimates of forest structure and composition, especially ones that span political borders and are consistent in their methodology, especially in this region here, going from Southeast Alaska all the way down to Washington. So that's kind of our aim of this research, is trying to create those structural estimates. We made really high resolution, 30 meter resolution gradient nearest neighbor imputation estimates of forest structure and composition. And then from those estimates, we also determined the spatial, or determined the drivers of the spatial patterns that we were seeing. So here's a map of the different modeling regions in our study, kind of the northern area, the West Kenai, which is more boreal than it is temperate. And then we have the south central part of Alaska, southeast Alaska here in red, which is the Tongass, a modeling region for northern British Columbia and southern coastal British Columbia. And some of you in this room might know what gradient nearest neighbor imputation is, but just in case, I'm going to go over kind of like how gradient nearest neighbor works. So let's say we have our landscape. I'm sorry I drew these on my iPad, so they're not like as pretty as they probably could be, but let's say you have this landscape, and on that landscape, you have a plot system. So let's say FIA, which was represented by those orange dots. You go out and collect a bunch of information about species composition and structure at those plot locations, and you get this nice little table that looks kind of like this, and that gives us information about biomass, let's say, per species at these sites. You can then go and collect a bunch of spatially complete data, like remotely sensed information, say Landsat, or environmental data, this maybe soil data or topography data. And then over those plot locations, you actually extract the environmental conditions that those plots experience. So you get another table that kind of looks like this, with all the different environmental conditions that that plot experiences. You can then relate those in gradient space. So we use canonical correspondence analysis to create an ordinational space which relates those species data to the environmental data. And then this is kind of where the fun happens. You can take any pixel on that continuous environmental raster layer, pull the environmental variables out of it, plot that into the gradient space, look at the nearest plot in that gradient space, and impute the summary statistics. So let's say that these are the summary statistics right here from this plot. Impute those into your map. You can make this a little bit more complicated, actually. And let's say k equals 3, which means that we're using 3 nearest neighbors. So this example, we use 3. In our study, we actually use k equals 5. You look at the 3 nearest neighbors, you took the summary statistics from those plots, and you take the weighted mean, and then you impute those into your output map. So at the end, you get spatially complete estimates of forest composition and structure. So the plot data we use for this analysis, for the US, we use FIA, and that's what you can see in green here. And then for British Columbia, we use a similar data set, FAIB, Forest Analysis and Inventory Branch data, and that's what you see in yellow. And we did a lot of work. These are very similar data sets. They're not exactly the same. So there's a lot of work that went into going through the data sets and making sure that they represented all the same data that we needed to, and they were put together so that we can use them in this one analysis. And then for environmental variables, we used Landsat 8 composite. So that was kind of a big lift to make a large Landsat 8 composite with green, or like the best available pixel for the entire region. We also terrain corrected it, which really helped the outputs of our models. We also use Landsat 8 indices, some tassel cap indices as well, land cover from NLCD. For topography, we had elevation and slope, location, longitude, latitude, and then we had climate normals for the region. We also used a time sense disturbance layer that we calculated from Landbrenner. And then these are the 4 structural estimates that we made at the plot level. So each one of these we calculated from the plot data, and then those ended up being our resulting imputation maps in the end. So we have total biomass, total above ground biomass. We have total above ground snag biomass, above ground biomass for the major above ground tree species. So those are individual maps for each species, hence the species. Basal area, tree density, volume, and dominant age, and quadratic mean diameter. And here's just kind of a view of what those maps look like. Just 3 of them: above ground biomass, quadratic mean diameter, and trees per hectare. And you can see how on a longitudinal gradient, there's a lot of variability, and it changes as you go farther and farther north. So each one of these maps consists of the entire range from Kodiak Island all the way down to the border of Washington, and we have one for each one of these variables that you see to the left here. Here are some of the examples of the individual species maps. So green is the total biomass amount for that species, and then the purple dots you see is just where we see them in the observed plot data. So you can see that our imputed maps are constraining species to where we actually observe them in the plot data themselves. And we have 1 map for each one of these species listed in the table to the left here. So out of the environmental variables we chose, what really drove our predictions? Well, climate, topography, spectral data, they all kind of explain the same amount of variance in our output models individually. And then combined, if you look at climate and topography, or combined climate, topography, spectral data, they actually explain most of the variance in our output models in total. Tassel cap performed a little bit less well than I thought it would, but it also explained a large amount of the variance in our output models. So when you zoom in, you can kind of see how things like topography or slope or previous land management affected our outputs and our models. Here's kind of south of Juneau. You can see age dominant predictions. There's a recent harvest here, and you can see how that affected the total age of the dominant age of that stand. This is the Rainbow Island. You can see how well-drained sloped had higher amounts of biomass. You can also see remnant harvests here. And you can also see how muskags had lower total above ground biomass in the center area of Zrimbo Island. We also had zoomed in maps of the individual species predictions, so lodgepole pine up top and red alder here on the bottom. How do these models perform? They perform pretty well, with the highest performing imputation map being above ground biomass, and then kind of the lowest performing being snag biomass. And that makes sense, and it's kind of true for most GNN models. It's really hard to observe snags from satellite data, especially at 30-meter pixel resolution. There's not also a very strong climate tie to where we're finding snags and how much snags we see. So it performed a little bit less well than some of the others, but above ground biomass performed pretty well. And you can see a trend of a little bit underestimation in our higher values across the board and a little bit of an overestimation in our lower values. And this is probably just a result of the fact that we use weighted means in our 5 nearest neighbors. Also potentially pixel saturation from Landsat. As you get to the higher biomass values, it's really hard to differentiate what's a exceedingly high amount of biomass in a stand and then what stand has like a moderate amount of biomass. They just kind of look very green in a Landsat pixel. So kind of just a quick summary of our results. We now have spatially complete predictions of forest structure and composition across coastal Alaska and British Columbia. So that ranges all the way from Kodiak Island, like I said, all the way down to the border of Washington and British Columbia. And then when you combine those with gradient nearest neighbor maps that already exist from a group like Lemma, there are now spatially complete estimates that are consistent, are pretty consistent with the methodology in which they were created, that range all the way from Kodiak Island down to the border of the southern border of California. That wraps that up. My name is James Lamping. I am in the Terrestrial Ecosystems Ecology and Landscapes Lab. So if you scan that, you get some more information about our lab. And this research was funded by a National Science Foundation grant. Thank you very much.
Thank you, Dr. Lamping. If anybody has a question, we still have some time left for that.
Hi, Lucas Johnson here. I've got a quick question. So I'm familiar with like things like this where you're like doing regression with a single variable and you might optimize for something like root mean squared error on that particular variable. In this situation where you're going after like a whole bunch of different variables at the same time, what are you using to optimize the prediction algorithm? And I guess related to that, what knobs are you tuning or turning beyond your K value, if any?
Yeah, really, most of it is your K value tells you how much variability you're going to have in your outputs. So it kind of smooths your outputs. It also does something to your individual species where you might be over predicting the extent of your species, because now you might be seeing, like if one plot might not have it in one imputation, it will show up in another one. So then it says that it's present. So your present absence data might be a little overestimated. Other than that, really the fine tuning goes into the environmental variables that you're choosing that go into your model. That's kind of controlling the output the most from what I've seen.
Okay, thank you, Dr. Lamping. Thank you, Justin. So now we are moving to our next presentations, and our next presentation is titled Climate Smart Restoration Tool, Climate Forward Generalized Seed Transfer Guidance Informed by Vegetation Inventory Database. And this research tried to address the critical need for seed transfer guidance tailored to current and future climate to support restoration programs. Now, please join me in welcoming Dr. Elizabeth Milano to present their findings. Elizabeth.
Great. Can you hear me and the screen looks good?
Sure.
Great. So yeah, thank you for the introduction. So this work is coming out of the Maintaining Resilient Dryland Ecosystems program with RMRS, a couple of us up here in Moscow. as well as we are working with the Conservation Biology Institute here. Okay, just make sure I got my slides all set up. So generalized seed transfer is based on the principle that climate is the main predictor of local adaptation in plant species. So this is in contrast to an empirical approach, which measures species-specific responses to different environments, such as in a common garden experiment, or by using population genetic data to define seed transfer distances. Not every species has the research time or resources to rely on those empirical approaches. So we use a generalized approach, which uses climate data to identify appropriate locally adapted genetic material for seed transfer and restoration projects. So the generalized approach comes in kind of two flavors. You may be provisional with this panel on the left, the provisional seed zones, which uses temperature and aridity to define 64 different zones. This is easy to implement, but can be less accurate, especially near the boundaries, and increasingly complex when you incorporate climate change. We can also use a focal point approach, which is what our existing climate smart restoration tool works on, or how that tool works. So this here is a heat map that shows mid-century climate similarity to our focal point of Priest River Experimental Forest in northern Idaho. You can see that blue point up top there. So in this case, all of the orange areas are considered to be future analogous locations to the climate of Priest River. So these focal point approaches are more accurate and can be dynamic to accommodate climate change projections, but difficult to implement without a web tool. So I've been talking about climate. What data are we using? This is gridded downscaled monthly climate data from PRISM and WorldClim, and it's distributed through Climate NA, which provides 800-meter resolution data for both contemporary 30-year normals, as well as projected data for future climates based on different carbon emission scenarios. So they provide both directly calculated variables such as mean annual temperature and precipitation, as well as a number of derived seasonal variables such as summer heat moisture index and growing degree days, etc. So our existing web tool, the Climate Smart Restoration tool, is built using that Climate NA data, and it allows users to select a focal point location and decide which climate variables they would like to incorporate. This is currently implemented both in the Climate Smart Restoration tool, and if you may be familiar with the seed lot selection tool, they provide the same functionality. And these are both collaborations from RMRS and PNW. So this method works very well in localized areas, but can tend to overpredict for large regions and requires users to make educated decisions about which variables to use and which transfer limits to impose. Which can tend to lead to over-parameterization and can reduce the usability of the tool. So on the left, we have 2 climate variables here, and you can see how much kind of analogous region is being shown. And if you switch that to 4 climate variables, you're kind of significantly reducing your area, but sort of guessing on what those transfer limits are going to be. So for our updated approach, we will use the same focal point structure as the CSRT to define these future analog locations, but we're going to do it based on the climate distance of 19 climate variables and very little user input or decisions. So the approach is novel in that it also incorporates vegetation inventory plot data to provide species composition information for those future analog locations. So this additional context for seed transfer allows users to better understand what the site will look like by the mid-century and make more sustainable decisions in how to manage it. So this work has already come out this year in April, and you can find the data and scripts in the publication. However, we are in the final stages of web tool development, and we'll be releasing it in early 2025. So again, the novel aspect of this approach is that it harnesses vegetation inventory plot data across North America. primarily FIA and Canadian forest inventory data. We have over 200,000 plots that are in our reference database. We also pull from the Mexico forest inventory, as well as the BLM AIM dataset for shrubs and grasses mostly for those non-forested Western states. As a backbone, we also have a biomes shapefile with over 400,000 plots. These plots don't have species information, but do provide detailed biome descriptions. So all told, it makes for a reference database of 685,000 plots that cover most of the continent. The methods are simple in theory. We start with a focal location of interest, and we look up those future climate predictions in Climate NA. We then use a nearest neighbor algorithm to find climate analogs in our reference database of inventory plot data. So we essentially use the future climate data for our focal point and match it to the contemporary climate for our reference database. The metrics that we use is just a climate distance metric, which is the Euclidean distance of the 19 climate variables that we input, which include our direct annual temperature and precipitation, as well as those derived seasonal variables, such as growing season, frost-free period, summer dryness index, and the list goes on. So once we get our list of analogs with their climate distance from our focal point, we then categorize those analogs by a threshold distance into strong, medium, and weak analogs. These thresholds were derived from a set of reference points, which I won't get into the details, but essentially after the fun computer bit, we get output in the form of maps and species occurrence tables. So let's get into the results. This is Tiger Mountain in Western Washington State. The panel on the left has climate analogs identified for our contemporary climate. The yellow diamond indicates our focal point. And the color of those dots indicates the threshold confidence for each of our analog plots, as well as the green polygon, which indicates the total area under our weak threshold climate distance. So a common theme that we see, again, the panel on the left is our contemporary climate analogs. The panel on the right are our climate analogs projected for the mid-century. The common theme that we found from many locations is a substantial loss in climate analogs between the reference period and mid-century. If we compare that back to our current climate smart restoration tool, we see that the new method is a bit more refined than the original tool, which in this case is based only on 2 climate variables. And so this provides a set of high priority analog locations to investigate further, whereas the CSRT may be overestimating some of those analogous locations. Another example we have here is Blanca Peak in Colorado. And we can see the panel on the left. Our contemporary analogs are mostly in these mountaintop areas. In this map, the green relief is actually our elevation shading. So you can see in the panel on the left, most of those strong analog locations are found in mountaintop areas, whereas by mid-century, those analogs are found at substantially lower elevations and more downhill and more southerly latitude than our original point. So this is also reflected in our inventory plot data. So the first column here is the species occurrence for our contemporary climate analogs, and the second column is the species plot occurrence for our future climate analogs. And what we find in the first column is that there's a high preponderance of aspen, spruce, and fir, whereas by mid-century, our analogs have transitioned more to juniper, oak, and pinyon, which are these species highlighted in orange down here at the bottom. In non-forested sites, here we look at a couple different high and low elevation sagebrush locations around the Great Basin. And we found few to no climate analogs at our lower elevations, as seen here in panels A and B. This is contrasted to these high elevation sites, which returned quite a few mid-century climate analogs. So we can start to think about what might be driving this shift in elevation and how do we plan to manage these novel climates moving forward. In this case, we can dig a little bit deeper. Here we looked at 50 different sagebrush sites in the Great Basin and found a relationship between summer dryness index and the number of future analogs found. So where we see that locations with no future analogs tended to have an SDI or summer dryness index below 0.2, indicating that restoration of these sites in the future will be an uphill battle trying to figure out what this novel site will look like. This pattern is not a new discovery. Others have found similar things about kind of the amount of novel climates we're going to encounter in the future, which is sort of another piece of evidence along that way. So we do have many additional examples and case studies in our paper, but just a couple of caveats before ending here. Our thresholds are developed to assess the levels of transfer risk. So they're meant to match the adaptive strategy of the species. If you're working with a specialist species with a narrower environmental or climatic niche, then it would be good to only interpret or use these strong analogs for interpretation, whereas for a generalist, our weak threshold will generally be a conservative estimate. Secondarily, the plot availability that we have for North America, as I mentioned, we currently have 685,000 plots in our reference database. I know that I think we have around 20,000 AIM plots right now, and I believe there are 40,000 to be had total we'd like to incorporate, as well as harnessing the full extent of the FIA data. We currently only have grabbed forested tree species from those FIA plots, but there is a wealth of more information available for those plots. We'd like to figure out how to incorporate that, or which features of that would be most important in incorporating into the tool in the future. So lastly, to conclude, our approach identifies mid-century climate analogs from existing plant inventory and biome data. Uses can include seed transfer guidance, especially for species with limited genetic knowledge. It can help assess restoration risks and site vulnerability to climate change, as well as be useful in developing discussions about proactive strategies and thinking about vegetation transitions. Future work, as I mentioned, we do have a web tool in development. We actually just got prototypes to play with yesterday, which is very exciting. And we plan to be sending that out to a core group of users for feedback pretty soon, and hope to be releasing that under the same Climate Smart Restoration Tool URL as the existing tool is now. So keep an eye out for that in the beginning or kind of early in 2025. We have updated our climate data to the latest version for the CMIP6 RCPs. And finally, again, we'd like to really incorporate more inventory plot data, figure out what additional pieces from the FIA database we can use that would be useful going forward. So with that, I'll conclude with our acknowledgements. We are funded by a bill, we are funded through bill. And as I mentioned earlier, are collaborating with Conservation Biology Institute as our web developers. So I'll end it there.
Thank you, Dr. Milano. And you are really on time. Thank you very much. I really appreciate. So our next presentation is on Albedo evolution collected on FIA plot shows the importance of forest type on net climate impact. That's the title. And the research is focused on critical role of the reflectiveness of the earth surface in determining the forest impact on climate. So to talk more in details, Dr. Lucas Johnson is here. Please welcome him. Lucas, your floor is.
All right. Yeah, thank you for that introduction. And thanks to Elizabeth. I now have a ton to think about in terms of incorporating future climate into this work. Yeah, I'm Lucas Johnson, and I'm a postdoc at Oregon State University, but I work with the FIA unit in Riverdale, Utah. And today I'm presenting some work that I've developed with the support of the co-authors listed here, but especially Sean Healy and Zichang Yang. So to start with some context, going to dig into the idea of reforestation as a natural climate solution, a strategy for mitigating global climate change. And I'm sure we all know that IPCC has reported that the global community needs to achieve net zero emissions by 2050. And that's where natural climate solutions come in, and particularly reforestation. And this is not a new idea. Farjon and others released a study in 2018 reporting that among a suite of natural climate solutions, reforestation is the largest climate change mitigation potential within the United States. And the chart on the right there describes that. You can see reforestation at the top, with the largest green bar showing the largest potential for climate change mitigation in the year of 2025. Internationally, there's tons of support for reforestation through things like REDD+, specifically the plus part, the Trillion Trees program and the Bond Challenge, efforts coordinated by NGOs. Nationally, reforestation is mandated through the Replant Act and the National Forest Management Act. There's regulatory and voluntary carbon markets that direct funds to land managers promising reforestation, and there's state level plans and initiatives that promote forests as a tool to offset greenhouse gas emissions. There's also quite a bit of space within the United States to implement reforestation projects. Grant Domke and others reported that there's roughly 33 million hectares of productive forest land that's currently classified as understocked in the United States. There's a capacity to plant 1.4 billion seedlings in a year, so the opportunity is there. So with this as a backdrop, I want to focus this presentation. Our work targets managers interested in planting optimal forest type groups for climate change mitigation outcomes approaching 2050. And we're intending to assist in one of the most fundamental steps in any reforestation project, and that's deciding which forest type group or species mix should be planted. So once again, this is not a new idea. It's very likely that most land managers are already aware of the carbon benefits associated with reforestation, and they probably know which forest type groups they should be planting to maximize those benefits. However, there are other countervailing geophysical factors like surface albedo change, which may offset substantial portions of these benefits and may impact planting decisions. So how does surface albedo change associated with reforestation offset carbon benefits? This cartoon, courtesy of Sean Healy, describes the general idea, with forests being inherently darker than many alternative land covers like rangeland, and as a result, they reflect less energy or radiation back into space. So these arrows describe that idea, with rangelands showing a much larger arrow going back into space, reflecting a lot more energy than forests with that skinnier arrow. And reflecting less energy into space translates to warming of the planet's atmosphere via radiative forcing. So Sean Healy and others have a paper describing the albedo offsets of forests in the United States. They use Landsat 8 albedo data in concert with FIA plots to quantify the warming in carbon equivalent units resulting from albedo evolution of different forest types and ages, specifically the 30 forest type groups classified by FIA, indexed by 10-year age bins. So some detail on what they're doing. They use this Landsat albedo data to compute the monthly difference between albedo at each forested plot and its 10 nearest non-forest plot neighbors. They then convert that difference into a radiative forcing and annualize it over each year, and finally convert it into a carbon equivalent albedo offset value. Then with FIA conditions as weights, they estimate the carbon equivalent albedo offset for each forest type and 10-year age bin using the statistical properties of the FIA sample. And with this technique, they estimated that roughly 50% of the non-soil carbon benefits in the United States are offset by albedo impacts. So that's a rather substantial result, but how does this impact reforestation decisions? How might managers interested in planting for climate change mitigation use this information? Well, they also made this data that was behind that study, that came out of that study, publicly available on Zenodo. There are tables containing non-soil carbon stocks and associated carbon equivalent albedo offsets for each forest type, group, and 10-year age bin. And in this study, we use that data to investigate near-term, circa 2050 reforestation decisions, specifically which species mix or forest type should be planted to achieve maximum climate change mitigation potential in the next 25 years. And 2050 is an important timeframe given the pending net zero emissions targets for that year. The IPCC reports have transpired of many entities making corresponding commitments. But also want to highlight that we're not all that comfortable using current or historical data to project outcomes much further than 25 years from now, given the forecasted and ongoing global changes. So specifically what we did in this study, we used 64,000 hectare hexagons tessellated across the United States in concert with FIA species distribution data and the carbon and albedo data set I just described to investigate the general geographic patterns of where planting decisions will be most impacted by the consideration of albedo. The FIA distribution data provided the set of options, the existing forest type groups within each hexagon, and the Healy and Yang data provided the rankings of these forest type groups on the basis of carbon or joint carbon albedo. And we're particularly interested in where carbon optimal forest type groups differ from joint carbon albedo optimal forest type groups. And recognizing that this broad scale assessment, considering optimal forest type groups at the 64,000 hectare scale, does not account for site-specific factors like topography or other silvicultural considerations like fire resistance or merchantability. We also provide a standalone application ranking all of the forest type groups within each hexagon on the basis of joint carbon and albedo. And through this app, we aim to empower managers to leverage this information within the context of their unique understanding of project and site-specific constraints. And this image of the app here on the right sort of describes how it works. There's a means to select hexagons from the map on top, and in the middle you get a table ranking all of the present forest type groups by joint carbon and albedo, with associated estimates of non-soil carbon stocks, carbon equivalent albedo offsets, and associated uncertainties. On the bottom, we're showing time series of each attribute for the forest type groups in the table. The idea there is that users can understand the temporal consistency of the 25-year optimal choice, with the large caveat that the further out into the future one goes, the less certain this data becomes. So our high-level general results, I'm showing the optimal forest type group for non-soil carbon storage on the left, and the optimal forest type group for joint carbon albedo on the right. And largely what we see is the concentration of differences in the northeastern region of the United States, in New England, and the Lake States. And we see that the Maple Beech Birch forest type group is often optimal when considering albedo in this region. That's that pink color in the northeast on the right there. And to highlight this shift, I'm now showing the difference in joint carbon albedo benefits in units of metric tons per hectare for only those hexagons where considering albedo yielded a different decision. And again, the Northeast pops out, but what also stands out are those purple shaded hexagons where the impact of only considering carbon is quite large. And these hexagons, they show that planting the Maple Beech Birch group yields an additional 20 metric tons per hectare of joint carbon albedo benefits relative to planting the otherwise carbon optimal pine group. And this distinction makes sense. A deciduous forest type group like Maple Beech Birch would yield a better outcome than a coniferous forest type group when considering albedo. Deciduous forests drop their leaves in the winter, and in these regions, they often reveal snowy ground surfaces, which reflect quite a lot of solar radiation. And coniferous forest type groups are dark green all year round and thus have a much larger albedo cost. I also want to highlight that considering albedo at this time horizon does not yield a different decision in most of the United States. That's pretty clear given that most of the map is white, but considering albedo does reduce the climate mitigation potential of reforestation in general, and sometimes substantially. I also want to highlight the lack of a decision space in much of the intermountain and southwestern United States, as evidenced by these white or empty hexagons in this figure. In these regions, there's often only one forest type group identified by the FIA sample, and that's often the pinyon juniper forest type group. And this is important since these forests grow very slowly and accumulate carbon very slowly. As a result, when considering albedo, these forests have increasingly net negative benefits with age. Okay, so I mentioned an app, and I've got a little screen recording here to show how that functions. You can zoom in throughout the United States, and here I select a hexagon in northern Vermont, and you get results. You get these rankings of each forest type group on the basis of joint carbon albedo, with estimates of carbon stocks and albedo offsets out in that table, and then the time series on the bottom. So one more example, so you really believe me, panning across the United States and zooming in to Northern California and the Lake Tahoe area, selecting a hexagon in the Tahoe National Forest. And we now get a different set of results. California mixed conifer is recommended as the joint carbon albedo optimal forest type group here. Okay, let's see. So summarizing our results, we've demonstrated that albedo impacts on 25-year planting decisions are concentrated in the northeastern regions of the United States. We're considering albedo offsets together with carbon stocks recommends the Maple Beech Birch forest type group in place of the otherwise carbon optimal white red or jack pine group. We also recommend our reforestation support application that allows managers to explore localized forest type group rankings on the basis of joint carbon albedo benefits. And the idea is that managers can combine this information with their understanding of site-specific or project-specific goals and constraints. And lastly, more broadly, we want to highlight that fine resolution albedo data, which is not currently a standard data product, provides more comprehensive support for reforestation projects, which are targeting climate change mitigation. So with that, I'll say thanks to all of you for listening. Thanks to my co-authors for their support. I want to point out that you can access the carbon and albedo tables that made this study possible at that Zenodo link. You can access the prototype of the application I demonstrated at that link below. Heads up, we are eventually going to be taking the app down from that link and providing a downloadable version also on Zenodo. And I know I don't have the proper icons here, but feel free to take a screenshot if that's helpful. And yeah, thank you for listening.
Thank you, Dr. Johnson. We still have time for one more question. So if anybody wants to ask a question, we have time for that. Looks like you presented well and nobody has a question. Thank you so much. And now we are moving to our next presentations. It is titled as Enhancing the Capacity of Subnational Entities for Monitoring and Implementing Land Management Approach to Mitigate Greenhouse Gas Emission. And this research focuses on developing effective implementation and monitoring plans for climate change mitigation at local, county, and state levels. So, and this presentation is being presented by Dr. Richard Birdsey. So let's welcome him. Dr. Birdsey, the floor is yours.
Okay, is that coming through okay?
Now it's much better.
Okay, very good. My name's Rich Birdsey. I'm retired from the U.S. Forest Service, and much of my time with the Forest Service was with the FIA program, so I've had a pretty long history there. I'm currently a senior scientist at the Woodwell Climate Research Center, located in Falmouth, Massachusetts, and just want to acknowledge a few colleagues from the World Resources Institute, whom I've worked with for about 5 years on this project. When we started a few years ago, we were working with a group called ICLEI, Local Governments for Sustainability, and they did some surveys of communities around the country about their interest in including forests and trees in their greenhouse gas inventories. And you can see the pie chart on the upper left that nearly every community had some interest in including forest and trees, but as the bottom graph shows, very few actually did it. And the reasons are listed over on the right side of the screen. The largest reason was they had lack of guidance. They really didn't know what to do. Most of these folks compiling the greenhouse gas inventories had little knowledge of forestry, or if they had forestry knowledge, they didn't really know much about the carbon cycle or how to make estimates or so on. And others thought not enough data, the information wasn't really required, or they thought the land was an insignificant source or sink for greenhouse gases. And so the idea here is to add to a typical greenhouse gas inventory, which would have involved the major sources of emissions, energy, transportation, and so on, and add the land component, which is shown on the lower part of the chart here. And so when you, in this example, when you add the emissions from forests as well as the removals from forests, you get a little bit of a larger amount, or a larger reduction in emissions over time by adding in the land sector. It's not a huge amount, but it's enough to be significant, and the counties wanted to account for it. In some counties, it's a much larger proportion of carbon being taken up by the forest than being emitted by the infrastructure and the use of energy, especially the more rural counties. So we decided to develop an online tool, which we called the Land Emissions and Removals Navigator, or LEARN, with the idea that this would perform a rapid analysis of several different kinds of data sets from the Forest Service and the U.S. Geological Survey, would generate customized estimates for any area in the contiguous United States. It's part of the Global Forest Watch suite of tools that are maintained by the World Resources Institute, and that the methods follow Intergovernmental Panel on Climate Change and U.S. Department of Agriculture, Forest Service protocols. And so these protocols were adopted by the 3 organizations listed below. And in the first 4 years since the tool was available, we've worked with about 65 different communities and counties across the U.S. Via training sessions and one-on-one consultations about improving or adding forests and trees outside forests to their greenhouse gas inventories. And we've generally had a very good support. And some of them have included this data in their greenhouse gas inventories. Some have chosen just to learn a little bit about their forests and then consider what additional actions they might take and might like to undertake. Very briefly on the methods, we have very extensive documentation about the calculations and where they're derived from and so on. But very simply, we look at both the gains in carbon, that is greenhouse gas removals from the atmosphere. And I use the term removals a little different than FIA sometimes uses it. FIA would call tree harvest removals. We're talking here removals of CO2 from the atmosphere. So we take account of that, and then the losses, which are emissions to the atmosphere. And then we add the 2 factors together and come up with a net greenhouse gas flux. But we look specifically and individually at emissions and removals because they imply different drivers and suggest different potential management actions that might take place based on this analysis. So activity data represents a couple of things. It's a fairly generic term, but we're really looking at land cover change, which we take from the National Land Cover Database, or in some cases, higher resolution data. That gives us information about changes in forest cover, forest to non-forest, non-forest to forest. And then we look at forest that remains forest based on disturbance maps, which we were able to then classify the land into either no disturbance, disturbance by fire, disturbance by insects, or harvesting, or other things like wind are bundled together because we don't have a map available that's just harvesting. So harvesting becomes what doesn't get classified into these first 3 classes. And then we look at how these changes happen over an inventory period through a transition matrix such as shown here. The emission and removals factors are calculated for each of those activities based on the national FIA data. The factors are specific to region, forest type, stand age, and the selected inventory area. And we represent all of the carbon pools, that is above ground biomass, below ground biomass, litter, soil, and coarse woody debris. And below in these boxes, a little bit more detail about these calculations, but it's really summarized up at the top, so I'm not going to go through those details. Oh, I will point out that we do a little bit with trees outside forests, based primarily on data from Dave Nowak and his cohort, who's collected a lot of data in different cities around the country. So we added that in, but we don't really cover trees outside forests that are not in urban areas. Or if we do, it's based on urban areas, which might not be representative. We have a number of user-friendly features to the tool. So the user selects an inventory period. There are numerous options given in the tool, selects a county, or the user can upload a shapefile and do the analysis for there. We select a representative city to get data about trees outside forests. There are a number of maps and data layers accessible through the tool, so the user can kind of take a look at what's going on in their area. Have there been fires? Has there been harvesting? Is there a lot of land use change, and so on? So that's the learn function. The idea is to learn about the resource and what are the drivers and what are the impacts of those drivers. And then within the inventory area that's selected, we calculate custom emission and removal factors based on all of those FIA removal factors that were pre-calculated. Those are averaged depending on the area of forests within the inventory area, how much is in different forest types, how much is in different stand ages, and so on. Or we have a new option that's just being rolled out that would allow a user to update their own emission and removal factors if for some reason they have data that's specific to their area that they feel is more representative of how those forests operate. The tool generates a report. It's an 8-page report with graphics and text. It's all canned, so it just pulls data out of the calculations, but presents it in a useful way for the user to get a pretty quick idea of what's going on. And then we output a CSV file of the input and output data, so the user can then do additional calculations if desired. We're going to do a very brief demo for the county of Jefferson County in the state of Washington. And this is the splash screen that shows up when you go into the Learn tool. Well, actually, this is the splash screen here. And it just starts with a large graphic of the land cover from the NLCD data. And over here on the left side, you have map layers that can be looked at and so forth. So for example, one of the layers shows forest disturbances. And so this map here on the right shows in purple where insect disturbances have taken place recently, well, during the period 2001 to 2022, shows where insects are in purple, harvesting is in orange. So you can see that's more prevalent in the southeast. And then in the west, fires show up as red pixels there, and so on. So it gives just a little quick idea of that. Anyways, you then select an inventory area by picking through a list of counties. In this case, as I said, we picked for this little demo, Jefferson County runs through the Olympic Peninsula in the state of Washington. Then you could also choose here, instead of picking a county, to upload a file, a shape file. And then this is select the inventory period. We have a number of options kind of tied to the NLCD data, roughly every 2 or 3 years from 2001 to 2021. So the user can use this slider to pick an inventory period, or could run the tool several times looking at several inventory periods to get some trends. And then for trees outside forests, we have something similar with a few less options based primarily on the NLCD data. Another feature that's listed here at the bottom, which we're still working on, would be to allow analysis of mature and old growth forests based on some maps that have produced by Dominic Della Sala and others. So we're adding that in as a little separate analysis because of the high level of interest in management of mature and old growth forests. So then you click the button to generate the analysis. It takes a couple of minutes. A lot of calculations going on the server. Meanwhile, you can take a look at what's going on here in Jefferson County. A lot of change from forest shown in red pixels here. Some changes from non-forest to forest in dark green, and so on. And here's a look at the disturbance maps, the period 2011 to 21 in Jefferson County. Lots of insect activity here. A little bit of fire. These red stripes are some fires that occurred during this period. This area is very wet almost all year long, so fire is much less frequent. Fair bit of harvesting. A lot of these far western areas are private lands. And then up here in the northeastern part, there's a little bit of a more urban development there. And then selecting a city is in this case, I selected Seattle, Washington to be representative of the county. And that's it. Then we get some results. And I've circled a few of the things that come out of here. There's an analytical report that I mentioned earlier. There's a pending analysis of the area of mature and old growth forest, as well as whether those forests are protected or not protected. Are they in wilderness areas or are they in national parks and so on? And you have the options of viewing the full report or downloading the data. Then on the lower left, we can take a look at the carbon factors that were calculated for this area. We have the emission factors I'm showing here, fire, insects, other disturbances, forest to grassland, and so forth. And those are forests being converted to different categories. I'm not showing the removal factors here, but if you click that button, that's what happens. And then here's the basic inventory report in the middle, which lists the numbers. So undisturbed forests, removing a very significant amount of carbon each year. And then a number of emissions from insects, from harvest, from trees outside forests, and then conversion of forests to grasslands according to the cover. A lot of that, it turns out, in many areas is a temporary conversion of forest to grassland, because remember the cover map shows only loss of tree cover. It's not land use change. And so the analyst has to distinguish between those two. But what happens is you look at the non-forest to forest here, it roughly compensates for the forest to non-forest. And so those are grasslands or areas that had previously been disturbed or harvested, and then they're coming back to forest. So you need to do a little detective work to figure out what's really happening based on these different data sets. And then you get the 8-page report I talked about, which summarizes all the data, including a bunch of graphics, which I'm not going to show. This is just a repeat of the previous screen. And just a note here that Jefferson County, we worked with them for a while, and they actually looked at, within their county, 8 different domains, mainly according to ownership. So they wanted to separate out the public lands from the the federal lands, I should say, from the county lands and from the private lands. And so they did analysis for all these different files, and they looked at 3 inventory periods 2001 to 26, 2006 to 2011, and 2011 to 2016. Jefferson County lands, and then the county minus the National Park Service and the U.S. Forest Service wilderness areas, and came up with a lot of numbers that they use to analyze their land. So here's kind of where we're at, and I'm almost done. We're updating the base maps to the most recent available ones. We're extending the available inventory periods to near current time, updating the report graphics and the files. We're allowing the user to override emission and removal factors. We're looking at mature and old growth forests. In the future, we've had a lot of interest in expanding the tool to include agricultural land so that the counties could have a complete analysis of their land base. And then we'll sometime in the future do some additional training sessions. So that's it. Thanks a lot. Willing to take questions now, or you could send emails either to myself or Aaron Glenn. And if you'd like to try out the tool, it's pretty self-explanatory. There's lots of tool tips in there, and it's kind of a neat way to get a first pass look at the greenhouse gas inventory for trees and trees outside forests. It's not accurate enough for assigning value to carbon credits. It truly is a learning tool. Gives you an idea of what to look at in more depth and explore with additional data or analysis. So I'm going to stop right there. Thanks for your attention. Maybe there's time for questions.
Thank you very much. I really appreciate it. We are heading to the break, so I just give you extra time to finish. And so with this last presentation, we conclude our session. And if you have any questions and any concern about all the presentation and the content of the presentation, please reach out to the particular presenter. They did a fabulous job. They really did a great job. Joe and I would like to extend our heartfelt gratitude to all our presenters. Your invaluable insights and pioneering research have provided us with a deep understanding of a lot of topics and innovative methodologies. And Joe and I also want to thank our audience for your engagement and thoughtful participation. I know many of you have a question, so if you have a question specific to a presenter, please reach out to them. That's the best way for the communications. And really, your presence and interest are what makes session like this more truly impactful. And we are hoping for similar session in other session as well. Let's give our one final round of applause and thanks to all our presenter and our audience. Thank you very much for your outstanding contribution. Thank you very much and enjoy your day. And if you have any question, you still can stay here and ask with the presenter.